Welcome to the video for Lecture 29, Section 1. This video covers controller tuning for a boiler that uses cascade plus feedback control. The main reason for using a boiler example is to provide a physical case or framework for what we're doing. One thing to remember about boiler is that they are a slow process. It commonly takes a fairly long time for the water temperature in a large boiler to change in response to a change in the fuel input. Boilers have a lot of thermal mass. For this boiler example, we are using biofuel to heat cold water. The amount of heat input is controlled by controlling the fuel flow rate. The boiler has many elements we had in the water heating case that we have used throughout the course. For example, the cold water flow rate through the boiler and the cold water temperature can change. As before, we will measure the heated water temperature leaving the boiler and use that to adjust the fuel flow rate. This is our feedback control loop. It is also our primary loop. The temperature sensor that measures the heated water temperature is used to control the fuel flow rate. The actuator is a continuously adjustable flow valve in the fuel line. There is one problem with our fuel line, though. In the upstream, there are pressure fluctuations that make the flow rate through the flow valve variable. So we are going to add cascade control. This slide shows our boiler with a second sensor that we will use to add cascade control. The second sensor is a pressure sensor that measures the upstream pressure fluctuations that cause the fuel flow rate to fluctuate. As the fuel flow rate fluctuates, the amount of heat added to the water fluctuates and the hot water temperature fluctuates around the desired set point temperature. And with boilers having so much thermal mass and being so slow responding, we can expect that adding cascade control will help the system respond to the process and set point changes quicker. Here is a block diagram for the biofuel boiler. The inner loop with the transfer function H2 connects a pressure sensor to a second comparator that adjusts the output from the primary controller G1. So our block diagram has two sensors. One is the pressure sensor. The other sensor is the temperature sensor on the outlet. We have two sensor feedback transfer functions, H1 for the temperature sensor and H2 for the pressure sensor. Both provide input to the flow valve adjustment. We have two controller transfer functions. G1 is the primary loop controller, and we will use PI control for it. The other controller is G2, and it's a secondary loop controller, and we will use proportional control only for it. So our question is, what does A describe, which is after the summation sign? What block diagrams can tell is about information flow and material flow. This is a good time to apply this concept. So what does line A between the summing point and the G4 transfer function describe? Well, this might be a good time to review some of the block diagram elements and what they are. G3 is the actuator, which in this case is the flow valve that is used by the controllers to adjust the biofuel flow rate. G4 describes the boiler and the controlled input to the boiler, which is the fuel. So the small a describes the fuel flow from the actuator to the boiler. The first thing we need to do to analyze the process and find the time-dependent temperature response to step changes in process inputs is to simplify and reduce the block diagram and collapse the inner cascade control loop. We did this before in section 19 of the course packet. We start by writing the servo and regulator expressions for the output A for the inputs P and F within the encircled section of the block diagram. For the input P, the transfer function is G3 times G2 over 1 plus G2 times G3 times H2. For the input F, the transfer function is 1 over 1 plus G2 times G3 times H2. Combining the two produces the expression shown here. To simplify things even more, we define two transfer functions, G5 and G6. which we will use in the simplified block diagram. Here is the equation for after collapsing the inner cascade control loop using the newly defined transfer functions G5 and G6. Also shown is the simplified block diagram with these new transfer functions. With the new transfer functions, we have eliminated the inner cascade control loop. Now, we can write the overall transfer function of the regulator and solve problems in terms of the different transfer functions G1, G2, G3, G4, G5, and G6. Now, we need to define all the transfer functions based on the information given. With cascade control, it is common to use PI control for the primary loop controller, which is G1 in this case. So we can define G1 to be Kp1 times tau I times S plus 1 over tau I times S. Proportional control is commonly used as the control mode for the secondary cascade control loop. So G2 equals Kp2. At this point, we don't know Kp1, tau I, or Kp2. These are the terms we will find through the tuning process. We will assume that the biofuel flow valve is described by a first-order transfer function with a gain of 0.5 and a time constant tau equals 1. We also assume that the boiler is defined by a first-order transfer function with a gain of 0.2 and a time constant of tau equals 2. Here are the expressions for G5 and G6, which were originally defined in terms of G2, G3, and H2. After we substitute the given terms and simplified them, we get G5 equals K5 over tau 5 plus times S plus 1. Similarly, G6 becomes tau 3 times S plus 1 over tau 3S plus 1 plus K3 times Kp2. Kp2 is the proportional gain in the inner cascade loop, and a value that we need to find through the control tuning process. This is a good time to see how Kp2 and cascade control impacts the overall boiler response. When we make Kp2 larger, tau 5 gets smaller, which means the system responds faster, because tau is the time constant, and if the time constant of an element is smaller, the system response is faster. And if Kp2 becomes larger, then G6 becomes smaller because the denominator gets larger. When G6 becomes smaller, it means that the flow rate fluctuations are moderated. G6 is the transfer function describing the fuel flow, and we can expect better overall response if the fuel flow rate fluctuations are moderated. The common practice with cascade control is to select Kp2 based on relation between tau 3 and tau 5. Tau 3 is the time constant for the flow valve. Tau 5 is the derived term that was produced when we collapsed the inner loop. The guideline we will use is that tau 5 is 1/10 of tau 3. So we were told that tau 3 equals 1 and K3 equals 0.5. So when we apply the guideline, we know that tau 5 equals 0.1 or 1/10 of tau 3. Then we use the definition of tau 5 to find Kp2 after we fill in the values for tau 5 and K3. We find Kp2 is equal to 18. Now assume that we are given a plot of the boiler output when the controller is disconnected from the system and we input a small step change in the input of magnitude m equals 1. With that, we find K, Td, and T using the Cohen-Kuhn method for tuning the controller. When we are done, we find that Kp1 is approximately equal to 54 and tau 1 is equal to 0.2. More details are in the course packet. Here are two graphs of the time-dependent boiler response. The left graph has cascade control and the right graph does not have cascade control. Please note that the vertical axis scales are slightly different, and the time axis scales are different by an order of magnitude. So without cascade control, we have higher overshoot, and we have many more oscillations, and it will take much longer for the boiler to settle down. So a simple cascade loop makes the boiler output respond much faster to a disturbance and have less overshoot. The course packet has a graph with both responses on one graph. This brings us to the end of Lecture 29, Section 1 video. Write down any questions you have and bring them up in class or lab.